Welcome to MEI Numerical Methods Solution of Equations 1. In this video we'll be looking at the bisection method. So supposing we need to solve the equation x cubed minus x equals 1, then the first step is to arrange it so that we've got a 0 on one side. So in this case all we need to do is write x cubed minus x minus 1 equals 0. Then we can see from the graph that there's a root somewhere between 1 and 2, i.e. where x equals 1 and 2. Normally we wouldn't know what the graph looked like, so a bit of trial and error might be necessary. So the next step is to consider the value of the function at either end of the interval. So when x equals 1, we can see that the function has a value minus 1, and at the other end of the interval, when fx equals 2, we can see that the function has a value 5. So we've established a change of sign in the function, and so with one exception which we'll be looking at in a moment, this is going to mean that the function crosses the x-axis somewhere between 1 and 2, and so if we call our root alpha, we can say that alpha has to lie between 1 and 2. So the question is, does this work all the time? And we see here we've got an example of a discontinuous function where if we were to choose the same interval, 1 and 2, then we'd have a negative value for the function on the left hand side and a positive value on the right hand side, which might lead us to, if we didn't know what the graph looked like, it might lead us to believe that there was a root somewhere between 1 and 2, but being a discontinuous curve, obviously that's not the case. So the next step in the process is to take the midpoint of our interval 1 to 2, so 1.5, and find out what the function is at that value. So that turns out to be 0.875, and previously we had our negative value of the function was minus 1, i.e. a distance of 1 from the x-axis, and at x equals 2 we were at a distance of 5 from the x-axis. So now we've got an improvement on that 5, we're now 0.875, so we want another change of sign, and clearly 1.5 is going to be a better value to have for x than 2, giving a value of the function much closer to 0. So we can say now that we're going to keep the left hand limit of x equals 1, and now we're going to change from x equals 2 for the right hand limit to x equals 1.5. So we've got a change of sign. So at that end we've got f of 1 equals minus 1, and at that end we've got f of 1.5 is 0.875. So that gives us a change of sign. And then we just carry on in the same fashion. So we take the midpoint between 1 and 1.5. So f of 1.25 turns out to be minus 0.29688. So now we've got an improved negative value. So whereas previously at x equals 1 we were a distance 1 from the x-axis we're now a distance of only of 0.29688. So we now choose 1.25 as our left hand limit, and then the right hand side we haven't got anything better than 1.5, i.e. 0.875 is the closest we've got to 0. So we've now got a smaller interval for alpha. So if you wanted to pause the video and have a go at continuing the process until you can find the root to 1 decimal place, and you might like to try using a spreadsheet for this, so we could show the results in a table such as this one. It's fairly flexible as to how you set it out. You could have the first column being x1 as here, and then the second column could be f of x1, third column could be x2, and the fourth column f of x2 as here. So whichever you prefer, but on the previous slide we got to the point where our interval was 1.25 to 1.5, and so we continue the process by taking the average of 1.25 and 1.5, so that gives us 1.375. Then we find the value of the function at x equals 1.375, and so that's a positive value, so that's an improvement on the 0.875. So we're going to ditch that one and replace it with so that was the 1.5, so we're going to replace it with the 1.375. That's our new value of x that gives us a positive value for the function, and then we haven't got an improved version for the negative one, so we keep the 1.25, and then we find the average of 1.25 and 1.375, so that gives us 1.3125. That gives us another even smaller negative value for the function, so that's going to replace that minus 0.29688 is going to be replaced by minus 0.05151, and the right hand positive, the x value that gives us a positive value for the function, stays the same. So we've now got an interval of 1.325 to 1.375, and then the process continues until we end up with alpha being somewhere between 1.3125 and 1.34375, and the reason we can stop at this point is that both 1.3125 and 1.34375 round to 1.3 to 1 decimal place. So therefore the alpha itself must round to 1.3 to 1 decimal place. Now, an alternative way of expressing the root is to take the midpoint of this interval. This was covered in an earlier video. You see, one of the drawbacks of the bisection method is that we've got lots of decimal places. Every time we take a midpoint, it makes so the values of x that we're creating in that column are getting the number of decimal places getting larger and larger each time, so that's one slight drawback. So we can state that our root is 1.328125 with a certain amount of error, and that error can't be any greater than the half the width of the interval, which is going to be 1.34375 minus 1.3125 all over 2. So that's the maximum absolute error that we can have that. Now suppose you've just got an equation that's already in the form f of x equals 0, and all you need to do is just confirm that there's a root of 1.84 to 2 decimal places. Then that's fairly straightforward to establish, because we just look at the widest possible interval, i.e. from 1.835 up to 1.845. So as we saw in an earlier video, that's the everything inside that interval rounds to 1.84 to 2 decimal places, and everything outside doesn't. So and if we consider the value of the function at the left-hand limit, that gives us that negative value there, and at the right-hand limit we get a positive value, which means, because of the change of sign, and strictly speaking we have to like to note that the function is continuous, so therefore it's going to be crossing the x-axis somewhere between those two x values. And so we've demonstrated what we needed to show, that the root was in fact 1.84 to 2 decimal places. Now the bisection method is quite a robust method, and as long as we're starting reasonably near a root, then by a process of trial and error we should be able to find that root. We've already seen the case of the discontinuous function. The other complication can arise if you've got a repeated root. So if the curve is just touching the x-axis, then you won't find a change of sign. And another complication is that if there are two roots lurking in a particular interval, you may find one and be unaware of the fact that there's another one there. Another advantage of the bisection method is that it automatically provides an interval for our root, so we can say that the root definitely lies within two particular bounds, or we can quote the midpoint of the interval and say that there's a certain maximum error. But as already mentioned, the one slight problem is that you can get lots of decimal places in the working. So that concludes the video for the bisection method, and we'll be looking at the false position method in the next video.